So let's say that we are dealing with the harmonic oscillator. The potential looks like this. If we plot it, it looks something like this. Okay, this is x, this is v of x, this is x equals 0. And we will show that the energy spectrum is discrete and is given by this expression. And we want to find the turning points. So what are the turning points? Let's say that this represents the lowest energy, E0. Then this point and this point, these two values of x, are the maximum positions for the classical harmonic oscillator. So once the spring gets stretched to this value, it momentarily stops, and then it starts to decrease in stretching. The object speeds up, right? The energy goes from potential to kinetic, and it's all kinetic here, and then it starts to go back to potential here, and it stops momentarily. The kinetic is 0, and so on. It keeps moving in this region. It can't extend past here and past there in the negative direction. And so those 2 points are the classical turning points where the particle sort of comes back. And so it can only live in there. Of course, quantum mechanically, it can exceed those values of x. And so we want to calculate those positions. So if this is the total energy of the system, we simply have to set this to potential energy and solve for the values of x. We'll get a positive and a negative solution to this. So let's solve for x. We get that, h bar omega, but we're dividing by m omega squared, so we have 1 factor of omega, and we take the square roots, and so we have plus or minus. Those are the two values of x that correspond to these locations. Right, we can solve them for different values of n. Right, so let's just do it for e equals E0 and E1, right, the lowest and the first excited state. What are these values? So for n equals 0, we can determine what these are from this. We get x equals plus minus the square root of n is 0, so this becomes 1. We just get h bar over m omega. So the value here is h bar over m omega square root, and here it's negative square root of h bar over m omega. And if we want to look at here, I made it a little too steep. We should be moving outwards a little bit. Sorry about that. Let's see if I can erase that. We're really moving out a little bit, and the same is true over here. So we're further away. All right, so these turning points are not the same as these. What are they? Well, they're given by this expression. For n equals 1, we have x equals plus minus the square root of, we get 3 halves in here. We multiply that by 2. We get 3 h bar over m omega. So square root of 3 h bar over m omega is this point, and negative square root of 3 h bar over m omega is that point. So x continues to, the turning points continue to increase in absolute value as the energy gets larger.